with that, good morning, everybody. Let's get started. So in the previous class, we looked at the stability, and then we start the discussion of the design of the filter. And we're going to be spending the second part of this course on the filter design. And in the previous class, we said we're going to be designing two types of filters. So hopefully it's clear to everybody what we're going to be doing. We're going to be looking at the recursive IIR filters, and we're going to be looking at the FIR filters, and we're going to be looking at different techniques of designing the filters. So before we start the filter design, we're going to do a simple example, and we'll try to highlight a few points in this example. So let's say we have a communication channel. And we want our receiver to pick up one of the signals. So if you look at the spectrum of all the signals that are available, we have a signal that occupies the band from negative 100 to 100. And we're going to assume this is W, which looks odd, isn't it? Like this is W and this is 100. Anybody knows why it's odd looking? Excellent. Usually, if it does not multiply by 2 pi, it's a frequency. If it is omega, it will be 2 pi multiplied, but nothing prevents us from having omega that is equal 100, and therefore the frequency is 100 over 2 pi. Okay, this is 200, and this is a 300. Okay, and the channel that we want to build is, so we have 3 channels. This is channel 1, this is channel 2, and this is channel 3. And the channel that we want to pick is the second channel. So I want my receiver to receive or process this part of the spectrum. So what do we have to do? We're going to design a bandpass filter. So therefore, we want to have a filter that's going to allow all the frequencies between 100 and 200 to pass through, and we want to remove all the other frequencies. And this is our H effective of JW. And this is W. Does that make sense? Okay. Now, what does this H effective mean? I mean, if you look back at the end of the previous class, if you go back to this class here, this is what H effective is. What does that mean? So we're going to take the signal, we're going to convert it to a digital signal, we're going to design a digital filter, we're going to convert it back to another filter. The equivalent of all this conversion is this H effective. Does that make sense? So if you are looking at the signal from a continuous point of view, all what happened to the signal is it went through HF vector. Make sense? Okay. So we come to our filter here. And let's say we want this magnitude to be equal to a 1. If this is the filter that we're going to implement, how can we implement this filter? And assuming this is an ideal filter, we're going to take this frequency that is a continuous time frequency. We're going to map it to discrete time frequency. So we're going to come here and we're going to map this to our discrete frequency. And therefore, we're going to need to know what sampling frequency is being used with the signal that we are trying to filter. So let's assume omega sampling is equal to 800 radian per second. Together? So we have a discrete time signal that has that spectrum. It's sampled at this rate, 800 radian per second. And therefore, the sampling time, t, is equal to 2 pi divided by 800. Omega is equal to 2 pi multiplied by t. Okay. So therefore, we can map this filter response to discrete time frequency. So I can plot omega here. And this filter is going to look something like this. Something like this. It's going to look symmetrical. And what are these frequencies going to equal to? We're going to map these frequencies, the continuous time frequencies, using omega equal to W multiplied by T. So we're going to map these frequencies using omega equal to W multiplied by T. What is T? It is 2 pi divided by 800. Therefore, omega equal whatever the frequency W multiplied by 2 pi divided by 800 to get the discrete frequency. And this is going to give me my omega. Together? So we're going to come to this frequency. This is 100 multiplied by 2 pi over 100 is going to give me pi over 4. So this frequency has to equal to pi over 4. The other frequency is 200 multiplied by 2 pi over 800 is going to give me pi over 2. And the same thing here, negative pi over 4, negative pi over 2. And this is going to be h of e to j omega. Together? Is that clear, everybody?
Yeah.
Again, it is very important to keep this graph in mind in order to understand all this. We're designing this. So this continuous signal is sampled to get h of omega. Okay.
And then what would the amplitude of the discrete one be?
1.
Yeah, by.
Yeah, we're going to just assume the amplitude is equal to a 1.
And so like that would be like in the, like if it was given instructions, it would be unity gain.
Yeah, unity gain. Okay, so if I have a filter like this, now keep in mind, this is omega. What does that mean? This pattern is going to repeat. Together, but we're going to just put it here from negative pi to a pi. But this pattern repeats every 2 pi, but from negative pi to a pi, this is the pattern we get. Because it's discrete, it's going to repeat every 2 pi. Okay, so if I want to design, if this is the frequency response of the filter, what is this filter going to look like?
Sing.
Excellent. What can I sing? A sink, there's only one sink. How many sinks do we need? 2. Excellent. So in order to get this frequency response, if you remember from the first assignment, we can have a filter or h of n that has a square here minus a square here. That will give me a bandpass filter. So if I use an ideal filter, I can implement this with h of n equal to sine pi over 2 multiplied by n over pi multiplied by n minus sine pi over 4 multiplied by n over pi multiplied by n. This first term is going to give me a square here that ends at pi over 2. This is going to give me a pi over 4. If I subtract them, they're going to give me a passband between pi over 4 and pi over 2. Is that clear? Mm-hmm. Okay. So now that I have h of n, how can I implement this filter?
Convolve it with
Yes, I can convolve it. I can write the expression for this h of n. I can substitute different values of h of n and get what the terms of that filter are going to look like. So if I were to do that, I'm going to get h of 0 that is going to equal to 1/2 minus 1/4, which is going to equal to 1 over 4. I'm going to get h of 1 that is equal to 0.0932, h of negative 1 that is equal to 0.0932.
Why is h of 0 equal to 4?
plug in 0.
Yeah, plug in 0, it can be 0 over 0. We're going to take derivative of both. Okay. I can get h of of 2, which is going to equal negative 0.159. H of negative 2 is going to equal to negative 0.159. H of 3 is going to equal h. I could have written all of this the same, like with equal like this. Is going to equal to negative 0.181, and so on. This is going to go from negative infinity to infinity. Make sense? Okay. I can get h of z for this filter. What is h of z of this filter? I can just take these terms and since I know the terms of the filter, this is going to equal to 1 over 4 multiplied by z0 plus 0.0932 multiplied by z to negative 1 plus z to positive 1 plus or minus 0.159 multiplied by z to negative 2 plus z to positive 2, and so on and so forth. Is that clear? Where it's coming from? I know h of n, just a discrete time signal, and therefore, to find the z transform, I just calculate the z transform of the discrete signal. Of course, I don't have a closed form solution, but I have the first few terms. This is 0, this is n. Okay. Now if I want to implement a difference equation, what is the difference equation going to look like? That will implement this filter. Since I have h of z, remember h of z is y of z over x of z multiplying across. This is going to give me y of n that is equal to 1 over 4 multiplied by x of n plus 0.0932 multiplied by x of n minus 1 plus x of n minus plus 1 together minus 0.159 multiplied, let's bring it here, 0.159 multiplied by x of n minus 2 plus x of n plus 2. And this keeps going forever. Again, this comes directly from h of z. H of z is y of z over x of z. And therefore, y of z is going to equal x of z multiplied by 1/4, x of z multiplied 0.09, z to negative 1, z to 1, negative 0.15, etc. And we take the inverse z transform, it's going to give me this expression. Okay. If you look at this filter, what do we notice about this filter?
Non-causal.
It's non-causal. Excellent.
It also be a finite impulse response
Excellent.
because it's not based on any of the outputs.
Excellent. So if you look at this filter, the filter is ideal. And it has non-causal, and it has infinite length h of n, impulse response. Therefore, can we implement this filter? We cannot. Why can't we implement it? Because it goes on forever. Because this expression is going to go on forever. And therefore, at any point, if I want to calculate y of 0, I have to know x at infinity in order to be able to even calculate y of 0. Does that make sense? What can we do to, if I want to do a practical implementation of this? I can chop off terms beyond a certain point, isn't it? I can say, okay, I just want a filter that has 100 terms, and I'm willing to sacrifice a little accuracy for being able to implement it. Does that make sense? The more terms I add, the more accurate it is, but that means that I'm not going to be able to implement it. But still, the system is not causal. Every time I want to calculate y of 0, I have to know the term x of n at the end in order to be able to implement the filter. Does that make sense, everybody? Is that clear? Okay, so before we move on to the next step, before we continue, let's do a demo with MATLAB. And then we'll come back to this example. Now, if you look at the voice, what is the spectrum that the voice occupies? 20K or less. But where is the most of the information in your voice? 4K. 4K. Excellent. Okay, so let's do this example. I'm going to run it. And then we'll go over what it's doing.
Seashells. She sells seashells. She sells seashells. She sells seashells.
Can you notice the difference between the two?
Volume?
Volume?
Frequency.
But the quality, can you?
She sells seashells.
Okay. So let's look at what we've done.
That's the same recording?
That's the same recording, yes. So we have the filter that we said we're going to implement, the bandpass filter. the impulse response looks something like this. It's the same. Now this filter that we have here is going to have an effective bandwidth between 1,000 and 4,000 hertz. Okay? And therefore, when we pass the signal to it, this is the signal in the time domain, which is not very useful. Does this tell you anything? Not very useful. So we'll minimize it. That was the input of the filter. This is the output of the filter. So this is the sound that you heard the first time. This is the sound you heard the second time. Again, looking at it in the time domain is not very useful. So let's look at it in the frequency domain. So looking at it in the frequency domain, what do you notice?
It canceled out most of the stuff in the outside of the 1,000 to 4,000 range.
Excellent. So if you look at the signal occupies all the way to, I think, like almost close to 6,000 hertz. And the filter removed all the frequencies from 1,000 to 4,000. Make sense? Now somebody is looking at this is also confused, like, oh, why did the signal get bigger?
It's a different scale.
Excellent. So keep that also in mind. So this scale is different. This scale is smaller than this scale, bigger than this scale, so therefore this looks amplified, but in reality, it's the same size. Okay. Is that clear? Mm-hmm. So this is a demo. I'm going to copy the code and paste it just so when you study, you can, if you like, run it. And just copy this figure.
I think you got to click on the picture and make it outside the text.
I don't know if it's gonna let me do that.
Background picture.
Oh.
Or like a not line 6.
Didn't really have to, did it?
Well, let's see if we can move these back. Very good idea. Who suggested that idea? Excellent.
That one was pretty good.
It doesn't matter. I don't care if it looks good or not. It just meant to get your attention to run it. So even if it's not clear, it's probably better. So you'll be curious and say, oh, why did this work like this? Okay. Now, one thing I want to emphasize, going back to our example, is the following. Once we design our filter for a certain sampling frequency, that filter will have this effective response that is from 100 to 200 only at that sampling frequency. Together? So what that means, if I sample this signal, so this signal is sampled at 800 with omega sampling of 800, this filter, the effective filter, is from 100 to 200. If I sample this signal at another rate, then this effective is going to be different. And to illustrate that, we'll do another example if we were to change the sampling frequency. So we're going to see what happens. if the sampling frequency is changed to 400 radian per second, which means T sampling is going to equal to 2 pi divided by 400 seconds. So if I come back here and draw the original spectrum, so it was 100, 200, and 300. And this was omega. And this is the spectrum x of j omega. Now, if I want to see what signal is going to be filtered, I'm going to come to this omega, and I'm going to plot x of e to j omega. And if I plot x of e to j omega, same thing. Omega is equal to w multiplied by t, which is going to equal to w multiplied by 2 pi divided by 400. And therefore, omega is going to look something like this. I mean, the scale does not matter, but it looks shrank, but it did not. Okay. So this is going to equal to pi over 2. 100 multiplied by 2 pi over 400 is going to be pi over 2. And this is going to be my pi frequency. And this repeats. Keep that in mind. Together? Now the output of our filter is going to look something like this. My filter that we designed will filter the signal from pi over 4 to pi over 2. So therefore, if I come here and from pi over 4 to pi over 2, I'm going to be getting this signal. So the output of the filter is going to look something like this. This is pi over 2, and this is pi over 4. And this is y of e to j omega. And this is omega. Together? And therefore, if I transform this to the continuous frequency, if I convert this signal back to a continuous time signal, again, omega is equal to w multiplied by t. And therefore, this pi over 4 is going to translate to 50 radian per second, and pi over 2 is going to translate to 100 radian per second. And therefore, my output is going to look something like this. And this is y of omega, or y of j omega. Together?
Don't you have noise because you didn't sample at the right Nyquist criteria? Like, if you're not sampling fast enough, the highest frequency is 300 here, right?
The sampling frequency is 400.
Sure. So that means 200.
Yes, I mean, there might be also aliasing that is caused by
Okay.
these elements. A very good point. Yes.
Anyways.
But for that, excellent point. Yes. But just worrying about what's going to happen to the filter, so just focusing on what the filter is going to pass it through, is going to have an effective filter that looks something like this. And that, sorry, that applies whether we made the frequency smaller or we made the frequency larger. So H effective of W is going to be from 50 to 100. Together? Does that make sense, everybody? So once we designed the filter, we wanted to filter the signal that was triangular. We designed the filter for that frequency, for 800 radian per second. If I go and change the sampling frequency, that filter will still work. However, it will be filtering the wrong part of the signal. And you can always know what part is going to do by following steps that are similar, converting it to omega and seeing what that effective omega is going to be. So the effective filter is going to look something like this. So therefore, just to add to that, once a filter is designed for a particular frequency, if the same filter is used with a different sampling frequency, the effective continuous filter would change. Okay. And since you pointed out there is also aliasing here, I'm going to add here plus alias signal. Which might look something. This is 300. Some alias signal. Okay. So we're going to start now that we understand that. Sorry.
I didn't finish writing the once filter design.
Now we understand the impact of the sampling frequency, and we agree we're going to design the filter for a certain sampling frequency. We're going to start looking at the filter design.
So, can you scale, if you change your frequency or your sampling rate, it seems that you could analytically just scale your difference equation so that it will still work, right?
What the scale meaning?
Well, like move it, right? Because to get the same effectiveness, right? Or no?
It's going to have a different. I mean, the difference equation that we generated from the original filter was this pi over 2 over pi over 4. So if you're going to change the sampling frequency, this is going to change. But that's the same thing as designing a new filter.
Okay.
Does that make sense? I mean, this pi is coming from this transformation. If this changed, then this has to change. Make sense? Okay. So let's look at the first filter group that we're going to be designing, which are the IIR filters.
The IIR?
IIR. Infinite Impulse Response Recursive Filter Design. And we're going to be looking at 3 design methods. The first method is it's called pole zero placement. And this is done directly in the Z domain. And in this method, we select poles and zeros to achieve the approximate desired frequency response. Now this method has advantages which is it is a simple approach. So the advantage is simplicity and we can use a graphical approach to design it. And it has disadvantage in that it is not optimal. And there is no recipe per se to follow in order to design the filter. Together? So the first method is the pole zero. We're going to be looking at it and doing examples on it. But this is the way it works, is we place the poles and zeros in order to achieve a certain frequency response. The second method that we're going to be looking at is continuous to discrete transformation. And as the name implies, what we're going to do is we're going to take a continuous time filter using classical method, and then we're going to transform that filter to the discrete time domain. So a continuous time filter is designed using classical design methods.
Is this like RLC?
No, like Butterworth, GP-chip filters, all these filters. And then the filter is transformed from H of S to H of Z. How do we transform the frequency response from H of S to H of Z? We're going to be looking at three methods. So the first method is called impulse invariance. The second method is called bilinear transformation. And the third method, it's called matched Z-transform. Okay. So the advantages of this method is the filter are near optimal. And there are clear design steps. And the disadvantage it is more difficult to design. And we must consider aliasing. Okay. The third method is using direct design. And in this method, we achieve the frequency response using a recursive minimization of an error function. Achieved. Okay, so the third method, we're going to have a desired frequency response, and we can tune the parameters. So we have a desired and we have the achieved frequency response. We take the difference as a cost function, and we keep tuning the parameters till we minimize that error between what we desire and what we are achieving. Make sense? So the advantage of this method is we can design any arbitrarily frequency response. The disadvantage, it uses numerical techniques.
It won't be optimal, right?
It might. I mean, depends on the cost function. Does that make sense? So you can try to achieve any shape you want, and there is a cost function between what you're achieving and the filter you want. And you keep tuning it till you eventually achieve, whatever desired frequency response you're trying to achieve. Okay. Now, one thing we're going to emphasize in all these techniques, and that is the filter order. And that filter order is a major concern. If I have a higher filter order, I can meet tighter specifications at the expense of more complicated filter. Does that make sense? So if you increase n, you can meet a higher or stricter specifications at the expense of more storage and more calculations. And we'll see that when we're doing our filter design. So in general, higher filter order we can meet tighter specifications, but at the expense of more complicated design and more prone to rounding errors. Okay. So with that, let's look at the first technique of designing the filter, which is the pole zero method. So this is method number 1 of designing an IIR filter, and that is pole zero IIR filter design. So who remembers the relationship between the poles and the zeros location and the frequency response of a system?
Poles you talked to infinity,
Remember when we plotted the unit
Not
circle
in the,
and we have poles and zeros, and we calculated the frequency response? We said we take the distances to the zeros divided by the distances to the poles.
yeah.
And therefore, when I am very close to a pole, what happens to that magnitude? It goes very up. If I'm very close to a zero, what is that magnitude going to be? Very small. So that's the idea. So from Z transform and discrete time Fourier transform, we know the following. If we have a pole near the unit circle, and if it is placed at an angle omega 0, will yield a frequency response that will peak around this frequency. And the closer the pole to the circle, what happened to that peak? The higher the peak. Together? Okay. Second, if we have zeros near the unit circle, at an angle omega 0, will yield frequency response that decreases around omega 0. And if we have a 0 on the unit circle, then the frequency response will be 0 at that frequency. Can we have a 0 on the unit circle? Yes. Can we have a pole at the unit circle? No. Okay. Okay, so a 0 on the unit circle makes the frequency response equal to 0 at that frequency. Okay. Finally, if we have a pole and zero at the same angle, but with different magnitudes, these will have only effect at the frequency where these are placed. So a pole, zero, placed close to each other. Oh, we're close at the same frequency, sorry. Placed at same angle. With different magnitude. Will have an effect only near that angle. So if we have a pole and a zero that are very close to each other, then their impact will be local. When I move away from them, their impact will cancel each other. But when I'm very close to them, they will have a big impact. Okay. So what are the design steps for designing a filter? Using the pole zero placement method. First step, we're going to determine the continuous frequency of interest. The desired continuous time frequency. And the second step, we're going to map to discrete frequency. Using omega equal W multiplied by T. And then we're going to place poles and zeros to achieve a desired shape. Then we're going to construct our H of Z. And H of Z is going to equal to, depending on the poles and zeros that you created, the multiplication of Z minus Zi, and I from 1 to Q, divided by the multiplication from I equal 1 to P of Z minus Pi. So we have Q zeros, and we have P number of poles, and Zi and Pi are the zero and the pole locations. Okay, finally, we select the multiplicative factor K. And the K is chosen to achieve a certain gain. And then we can test our filter. Is that clear? Steps? Straightforward?
What does it say at the end of line 3? Desired
Shape. Did you ask because you could not read it, or just to let me know that
I-
you are at this point of typing,
I didn't know
of
if
writing?
it said shape or slope.
Okay. Okay.
So is the number of poles and zeros the order here? Like the order of the filter? What determines?
the number of poles in the transfer function.
No, but it's a queue.
Okay. So let's look at some examples. Using the pole zero placement method. And we're going to look at low pass filter, a high pass filter, a band pass filter, and a band stop filter. So let's start with a low pass filter. What is the simplest low pass filter we can build? Okay, let me plot the frequency response to help you answer. So I want a frequency response that looks something like this. So this is a pi, this is a negative pi, and this is h of e to j omega. How can I build a filter that will give me this frequency response? Based on what the steps we said. If I want the frequency response to be a 0 at pi, then what do I need to have?
0.
A 0 at pi. So I'm going to have a 0 here. And if I want the frequency response to be very high at very low frequencies, what do I have to have? I need to have a pole very close to omega equal to a 0. Is that clear? And if we assume this is A, then h of z is going to equal to z plus 1 divided by z minus A. Together? What is the magnitude going to equal to when omega is equal to 0? No? When omega is equal to 0 at this frequency, what is the gain here? Omega equal to a 0 corresponds to z equal to a 1, isn't it? So therefore, I can just plug in z equal to a 1, which is going to be a 2 divided by 1 minus A. Is that clear? Makes sense? Okay. How can I implement this filter?
inverse C transform?
I can, and that will give me h of n. Or
Split into a different equation?
I can convert it to a difference equation, yes. Y of z over x of z, multiply across, and then put the terms together. It will give me the difference equation that will implement this filter. Okay, let's do another, let's do a high pass filter, similar to this filter. And later on, we'll do a numerical example. So this is a low pass filter. We're going to have a high pass filter. If we're going to have a high pass filter, then what is the gain at very low frequency? 0. So therefore, we're going to place a 0 here, and we're going to place a pole at this distance here. So this is A. So therefore, h of z is going to equal to z minus 1 divided by z plus A. And therefore, the frequency response is going to look something like this. So this is h of e to j omega. This is 0, and similar to what we've done before, what is the gain at this point here? What is the magnitude at this point? Okay, I'll write it and you tell me why. Why is it 2 over 1 minus a1?
You put in pi?
I put in omega equal to a pi,
That'd be -1.
but z is going to equal to -1. Omega equal to a pi. Remember z e to j omega. When omega is equal to a pi, z equal to -pi. So -2, -1 minus 1, -2 over -1 plus a. Make sense? And then minus cancels. Okay, let's do a band pass filter. Okay, so the frequency response that we want is something like this, rougher than that. Okay. How can we get a frequency response that looks like this?
Low pass and a high pass?
Very good. So what do we have to do? We have to place 2 zeros. Where are we going to place these 2 zeros?
Close to the cutoff frequency.
How about a 0 here? Where's the other 0 going to be? And I should have labeled this correctly. This is a pi. This is -pi. The other 0 is going to be here. So it's going to be 0 at low frequency, 0 at high frequency. And in between, we want it to peak at certain frequency. So I can place a pole here and a pole here. And this pole is at omega 1. And the distance is a. And therefore, h of z is going to equal to z minus 1 multiplied by z plus 1 divided by z minus a e to j omega 1 multiplied by z minus a e to negative j omega 1, which is going to equal to z minus 1 divided by z squared minus 2a cosine omega 1 z plus a squared. Together? Make sense? Okay. Finally, we're going to design a band stop filter.
The zeros be on the vertical axis.
Let me plot the frequency response first. How is that? Okay, so what we want this to look like is something like this. And it's symmetrical, but okay. And this is omega 1. It's a band stop, so we want to remove this frequency. Now, of course, these are the simplest. We can make them fancier. We'll see later. What do we need to do to remove this frequency? We're going to put a 0 at omega 1. So this is omega 1. There is a 0. And then we're going to place a pole somewhere here. So this is A. So therefore, h of z is going to equal to z squared minus 2a cosine omega 1 multiplied by z plus a squared. Divided by z minus a1, or z minus a.
Why is there only one pole?
What, you want more poles?
Every other one had more than one.
I mean, you can, as we will see, you can put as many poles as you want. Each pole is going to come, is going to affect the frequency response, but the simplest.
You just put that pole there. Like, why did you put it there?
Excellent question. Why did I put this pole here when I could have just had this numerator?
Because to increase directly between, we had a max directly between.
Is it like Q factor? Is it the steepness of it?
The one will answer this question will be the start for till the end of the month. And the question is, why did we add this pole when we could have just a numerator like this?
Because a pole might exist.
What else?
It prevents it from just being a
Yeah, it has
level
to do
line.
with the distance.
You guys not gonna know the answer.
I know what is that. It's the poles.
And I don't say it in a mean way, but because we did not see the, you won't know the answer now, but hopefully when you see the FIR filter, you're going to remember this, and the answer will become okay. Because we're designing an IR filter. If I remove this from here,
Be an FIR.
then I'm going to be getting an FIR filter. Does that make sense?
That
Who
makes
was going to
sense.
say that? But later on, we'll see the FIR filter. We'll do something like this without any denominator.
Mhm.
And somebody is going to ask, why is there no denominator in here? What will the answer be?
It's finite.
Because it's an FIR filter. So for an IR filter, for this to be an IR filter, I have to have a pole. Because when I multiply by y, I'm going to get a y that depends on another y. Does that make sense?
Yeah.
If there was no denominator, y over x, then y only depends on the input. Becomes an FIR filter. Okay, very good question.
But why'd you put it there?
Why on that axis is that full layer on that?
Like, could you have put it over on the other side?
Yes, I could have placed
So
it
it's
anywhere.
negative.
A
Yeah,
could
A
have
could be
been
negative. A could be
placed
negative.
anywhere. It
A
will change how this frequency response is going to look like.
Mhm.
Does that make sense? So
Yeah.
depending on where you select A and the value of it, is going to change how the frequency response will look like. Again, we'll do a numerical example where we are interested in removing particular frequency, and we'll see where we place the A. If there's no other requirements, you might choose the A based on the gain of the filter. So if there's no other requirement, we know this magnitude here is equal to 2 minus 2 cosine omega 1 divided by 1 minus A. So you might choose the A, so it gives you a certain gain at that frequency. If you might choose the A based on the value here, which is going to equal to, this is 2 plus, which is a 2 minus 2 cosine omega 1 divided by 1 minus, or minus 1 divided by A. Okay. Is that clear? Makes sense? Everybody? Okay. Okay. Now, one thing to keep in mind is that when we place a zero or when we place poles or zeros, if they're complex, they're always going to appear as conjugates of each other, so that the frequency, the filter, the coefficients are real coefficients. And one other thing we can do is if we can place multiple poles and zeros near each other. And if we place multiple zeros or poles near each other, that will lead to a flatter frequency response. So for instance, if I want to design a filter a bandpass filter, so using a single pole, we got something that looks like this. What if I want to make this smoother or flatter, sorry. So I can place multiple zeros. So I can come here, place zeros, a zero, a zero, a zero. I can multiply, add pole, a pole, a pole, pole, a pole. And that will generate a frequency response that might look something like this. Make sense? Okay. We can also achieve a sharper response And in order to achieve a sharper response, we'll wait till Wednesday's class. Let's stop here. Any questions?